Hello everyone once again. I just wanted to give you a quick lesson continuing our conversation about humidity. And that lesson's going to be about relative humidity. Now, if you recall from our earlier lesson today, just as a quick review, and for those of you who were not there, which I think a majority of you were, um, this is what we talked about. We defined humidity, which we have done before in class. We defined humidity as the amount of water vapor which is its gaseous state that is in the air. But something to keep in mind, and something that's going to be really, really important in terms of understanding humidity, is the fact that water as a vapor, water as a gas, is when those individual water molecules are not touching each other. The key there is that they are individual. This is what allows them to be invisible. This is why we cannot see water vapor. Now, where many students and a majority of the public get confused about water vapor is that it is not clouds, okay? A lot of people think that clouds are gas. A lot of people think that fog is a gas. They are not gases. Just because you can breathe them in does not mean that they are a gas. Those are liquids, and in some cases they are solids, depending on what the temperature is. I think a majority of people understand that rain, sleet, snow, and hail are most certainly liquids and solids and not gases. So when we're talking about water vapor, we're talking about those individual water molecules free floating in the air. I took some time to describe the chemistry behind that and how water is polar and sticky and kind of like a magnet. That's going to come back into play when we talk about our two different types of humidity, of which we defined as being absolute humidity, something that is not that common, okay, and something called relative humidity, which we're going to talk about today. Before we do that, let's just quickly give an overview of what absolute humidity is. Remember, it's the actual amount of water vapor in the air. What we're really doing here is how many grams per given amount of air. Now, in this example, it says 30 grams per meter cubed. The actual way that they are measuring it is not through that. It's essentially saying how many grams of water are there in 1 kilogram of air. That's really what we're trying to answer here. Is it useful? Well, the answer to that question can be yes and no when it comes to weather, and I know that I said this to a couple of the periods that I taught. When it comes to weather, absolute humidity is not really that big of a factor because it can vary so much, not only depending on where you are on Earth, but also your temperature throughout the day, as well as the rate of evaporation, as well as your elevation. There's a lot of different factors that play into this. This is something that we can feel when we breathe in, but it's not necessarily anything that's going to help us determine whether it's going to be sunny, cloudy, or rainy, and that's really what we're concerned about, right, when it comes to weather. We look on our phone. What are we looking for? One, we're looking for the temperature. We're seeing how warm it is outside. And two, we're saying, hey, is it going to be sunny out? Is it going to be cloudy out? Or is it going to be raining out? And absolute humidity does not give us any clues as to whether that is the case. What does give us the clues, and is really the first step in this unit towards you becoming a really good meteorologist, which is somebody who can study the weather and predict the weather, is understanding how relative humidity works. Okay, I'm going to pull up my slides here. We're going to go through relative humidity. I know a majority of the answers are already here because I don't really want you to think about writing those words down and think about what those words mean, but rather having this be something that is very visual to you, which is why I'm going to be providing you with a couple diagrams to help you understand it. But also I'm going to be showing you a demo at my house here to help you understand what relative humidity is. So let's go back over here. Let's pull up relative humidity. Let's talk about it. So, what is relative humidity? It is a ratio. It is a percentage. Okay. Now, before we were saying that absolute humidity or specific humidity is the amount of moisture in the air. Okay. Well, we can measure how many grams it is, but that doesn't mean anything because each amount of air can hold a certain amount of water vapor. So, what we are going to do is we're going to take that absolute humidity, the specific humidity, how many grams of water vapor there is in the air, and divide it by how much that air can actually hold. And the thing is that different types of air can hold different amounts of water vapor. Now this is based upon something. Okay, we're going to fill that in later. We're going to fill in that basic idea later. Okay, so it's a ratio, it's a percentage. When we go back over to our notes, we see, yeah, it's a ratio or percentage. It's how much moisture in the air. Hey, that's absolute humidity. But this relative humidity is divided by how much moisture the air can hold. This is based upon something, and we're going to take a look at what's it based upon. So, how is it measured? Please take a look at this image right here. This is an image of a really weird tool that I was hoping that we would be in school to use. It is called a sling psychrometer. Very weird type of tool to use, but this is the type of tool that we use to measure the relative humidity of the air. Okay? It's really cool, okay? We know that thermometers are used to measure temperature, right? Anemometers are used to measure wind speed. Barometers are used to measure air pressure. Maybe some of you did not know that. Well, this tool, called a sling psychrometer, is used to measure the relative humidity of the air, which is very important in terms of determining the weather. There are a whole bunch of different parts to it, okay? There are two thermometers, okay? This thermometer right here is just a normal thermometer. It measures the air temperature. This thermometer is also a normal thermometer, and without this piece, it would measure the air temperature, but this piece right here is a piece of cloth. And that piece of cloth is covering the second bulb of the thermometer, right? So here's that second thermometer, and we have this cloth covering that bulb. Okay. Now you'll see that that cloth kind of continues on into this, it's like a reservoir, kind of like a bowl of sorts. Okay. Inside of that bowl, what you're supposed to do is you're supposed to fill it with water. And that water, what it does is it will be soaked up by that sock. Okay. And that sock is going to get really, 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 really wet. And at the end here, you'll see there's this blue cylinder. That blue cylinder is a handle, and this whole thing is meant to be swung in a circle. Let me show you what that looks like. Let's do it here. Turned off the sound because it's got really annoying music, so pull ahead here. Yeah, so we have this regular thermometer, which is called the dry bulb. I'm going to go back and pause that for a second. Got that regular thermometer that I previously described before as being the dry bulb, and then here we have still a normal thermometer, but this one is attached to a piece of wet cloth, and it stays wet because there's a reservoir at the end. And you're going to see that these two people right here are taking some water from their water bottle, and they're filling that reservoir full of water so that you can get that cloth on the second thermometer to get really, really wet. Okay? Now what they're doing is they're timing how long that person takes that sling psychrometer and actually slings it, right? It's like lassoing, like a cowboy. You're going to keep on slinging it and slinging it and slinging it for about a minute, okay? Now, we already talked about in our previous topic in evaporation that wind increases the rate of evaporation, right? I'm increasing the friction on that surface layer. More of that surface layer is going to be popping off, and that's going to evaporate more. We also said that dry air evaporates more, right? So if the air is dry outside, would that wet bulb, meaning the thermometer with that little tiny wet cloth on it, evaporate more? The answer is yes, because dry air loves to evaporate. But we also said in evaporation that evaporation cools the surface of an object. Okay? So we should see in this reading right here that they have a wet bulb temperature of 24 degrees. Okay? The air temperature is actually much higher than that. You can see on their first thermometer it's 30 degrees. Why is that? Well, because this wet bulb was evaporating, because it was wet. Wet things evaporate, especially in dry air. And since evaporation cools the surface of an object, the wet bulb thermometer, the one that is covered in that wet cloth, is going to get much colder. If the air is dry, it's really going to get cold because more evaporation means it's going to get colder. If it's not that dry, meaning the air is very humid, then that wet bulb is not going to evaporate that much and the temperature is not going to be a drop of that much. What is this sling psychrometer measuring? It's measuring how dry the air is. So she's slinging it, really measuring the rate of evaporation. The rate of evaporation is able to determine how dry the air is, and therefore what the relative humidity is. Now we're going to be doing a lab later on, either at the end of this week or towards the beginning of next week, where we're going to be taking a look at some data from this sling psychrometer. Now normally we would be walking out throughout the entire school taking data points with sling psychrometers, but since you don't have any sling psychrometers and we're not at school, I'm going to be giving you that data and we're going to be taking a look at it. But take a look at that difference right there. The dry bulb temperature, which is the actual temperature outside, is 30 degrees. They had a dry bulb temperature of 24. There's a huge difference in temperature between that wet bulb and that dry bulb, which must mean a difference of 6 degrees is pretty big. That means that air must be relatively dry. We're going to take that information, we're going to bring it over to a chart, and I'm going to teach you towards the end of the week how to use this chart. It's pretty easy. And you can use this chart to determine what the actual relative humidity is. Okay? Now they're going to determine it. They bring it together. I don't know what they end up coming up to. 61%. So when they use that sling psychrometer, they come up with a 61% relative humidity. Now let's go back to our definition of relative humidity. See if we can figure out what that means. It's how much moisture is in the air compared to how much it can hold. And it was 61% full. So it could hold another 39% more moisture before it becomes full. And we used a sling psychrometer to measure it. Okay? Now, where things get a little crazier is something called dew point temperature. Now, dew point temperature takes us a step further. It's the temperature that condensation occurs and the air becomes saturated. Well, those two things mean the same thing. If dew point temperature equals that air temperature, then relative humidity is going to be 100%. Now, if we took a look at that previous video, they determined that the relative humidity was 61%. That means that no condensation is occurring. That means that the air is not saturated, meaning it's not full of water vapor. It's only 61% full. If I can get that relative humidity to be 100%, then I'm going to get condensation to occur, like on the outside of soda that's cold, like on plant surfaces in the morning, like clouds, fog, rain, precipitation. Okay? That can only happen when the relative humidity is 100%. It can't happen when it's 60%. It can't happen when it's 90%. When the air is full of water vapor, when the air has the maximum amount of moisture that it can actually hold, then relative humidity is going to be 100%. The air is fully saturated, but this can only happen at a certain temperature. Okay? And that temperature is called the dew point. Makes sense. If I can get a temperature where the air is fully saturated, then it's going to make dew. What's dew? Dew is condensation. Take a look. How can we get that dew point temperature? I have three scenarios here. I have a 30-degree air temperature in Celsius. It's like 86 degrees Fahrenheit. I think that's about it. 20 degrees Celsius and 10 degrees Celsius. I notice that there are blue dots in three scenarios here. This is showing you the amount of water vapor in the air. That's the absolute humidity, how much water vapor the air actually has. Okay? But you'll notice that there are yellow circles here. 30 degrees, 20 degrees, 10 degrees is the full size of the amount of water vapor that's in the air. The yellow circle represents how much water vapor the air can hold. I like to think of the yellow circle as a gas tank, where The blue circle is how much gas is inside of that gas tank. Well, when the air is 30 degrees Celsius, the gas tank's not that full. It's only 28% full. This means, that the relative humidity is 28%. The air is 28% full of how much it can actually hold. This is why the relative humidity is 28%. Now in 20 degrees, we notice that yellow circle gets smaller. And in comparison, the amount of water vapor in the air, which did not change, is a larger percentage of how much it can actually hold. Now it is 52% full. The gas tank is 52% full. It is 52% relative humidity. I drop the temperature down to 10 degrees Celsius and I notice that that water vapor is now the same exact size of how much it can actually hold. It is now 100% full. If that's the case, what is the dew point? Well, if dew point is the temperature at which condensation occurs, the temperature at which the air is saturated, and the temperature at which we have 100% relative humidity, the dew point is 10 degrees because 10 degrees is where we have 100% relative humidity, the air is full of water vapor, and it is fully saturated. Okay, this is where a cloud will form. This is the only scenario where we have rain that is possible. Okay, so how can we reach that dew point? Well, in our first scenario, we were at 30 degrees Celsius. Our amount of water vapor was the same as 10 degrees Celsius. To reach dew point, we can do a couple of different things. The first thing I can do is I can lower that temperature down to that dew point. Okay, where many students get confused is they say, well, isn't dew point a temperature? Yes, it is a temperature, but it is not the temperature. Okay, let's say outside it's 20 degrees right now and the relative humidity is 52%. What would the relative humidity be? Well, right here it's telling us that it's 10 degrees Celsius. Okay, so if I were to ask Siri right now, what is the dew point?
The dew point is currently 57 degrees Fahrenheit.
So the dew point is 57 degrees Fahrenheit, but outside it's 61 degrees. What does that mean? Well, it means if I can cool the air temperature outside to 57 degrees Fahrenheit, then a cloud will form, then fog will form. Now I look outside and I don't see any fog, but I do see that there is a cloud above me. Why is that? Because above me, it is 57 degrees Fahrenheit, because as you go up, it gets colder. So above me, the dew point has been reached. The air is fully saturated. There is 100% relative humidity, so therefore condensation is occurring. This is why we see clouds above us. Okay? To help explain this a little bit more, what I want you to do is I want you to go on Schoology right now, and I want you to look at the second attachment that I posted to this assignment. And there's a video there, and it's of a demo. I want you to stop the video and watch that demo, and I further explain this idea that you see in front of you here with this diagram. Okay, perfect. So, reaching dew point. An easy way to do that is to cool the air temperature and dew point is reached, okay? That's exactly what that diagram before was showing, right? Taking a look at that diagram, we were at 30 degrees, relative humidity was 28%. I cooled it down to the dew point at 10 degrees and I got 100% relative humidity. So I can cool the air temperature to the dew point to reach it. Now you guys done this all the time. You've seen it, but you haven't actually realized it happening in real time. Take a look right here. It's a classic example. Just taking a couple things of ice here, adding a little bit more water, and we're just making a cold glass of water. This is best seen in the summertime. Watch what happens to the outside of that glass. It starts getting foggy. You speed it up a little bit more. We've always seen you grab a soda from inside of the refrigerator, you pull it out in the summertime, and it's almost like the soda is raining. Well, It's not the ice that is melting. It's actually condensation, that water molecules are being pulled from the air and they are sticking on that surface. Okay, I'm going to pause it right here. Because this glass is super, super, super cold, it is cooling the air directly near it down to the dew point, so condensation starts to occur. But you guys know from making a cloud that condensation can only occur if it has a surface to condensate on. And since there's not a lot of dust that is near this glass, it only has the glass itself to stick to. So as time progresses, more and more condensation starts to occur on this cold glass of water, because that cold glass of water is cooling the air around it to the dew point, and the only surface to condensate on is that glass itself. Okay? So pretty cool idea of condensation. All I need to do is reach the dew point. One way to reach the dew point is to cool the air. Let's put that inside of the notes. We got a couple things to fill in here, don't we? So relative humidity, ratio, percentage, moisture in the air divided by how much the air can actually hold. This is based upon something. I'm going to keep this here for a second, and we're going to talk about that in a little bit. Hopefully by this point you have recognized what that is. It's measured using a tool, and that is called a sling micrometer. Okay, it's just this huge, well, it's not really that big, it's probably about 10 inches long, and it's got a handle on it, and you sling it around. Dew point, it's a temperature where the following occurs. There's a whole bunch of things that dew point will do. Let me just 1, 2, 3, pull these over. There are a bunch of things, and they all mean the same thing when it comes to dew point. A temperature where what occurs? Well, it's the temperature at which condensation occurs. For that to happen, we need the relative humidity to be what? It's got to be 100%, which means it's full of water vapor. Another way to say that it's full of water vapor, the air is saturated, which means full of water. Specifically water vapor. Now, for those of you who are understanding this so far, you might be saying to yourself, okay, I understand that I can lower the air temperature to reach that dew point, but can I get the temperature below that dew point? Well, if that were to occur, and you saw what I did in the demo, you recognize that the amount of moisture in the air, this numerator in our relative humidity equation, is going to go down because the beaker overflowed. And when the beaker overflows, there's less moisture in the air, so what's going to happen to the percentage? It's going to go down. When my numerator decreases, my overall fraction is going to decrease, so my percentage is going to decrease. So if the air temperature tries to get below that dew point, well, guess what? The relative humidity is going to drop with it, so the air temperature is not going to get affected because the dew point is going to drop with that air temperature. So the air temperature can never be lower than the dew point. Now, can it be higher than the dew point? The answer to that question is almost always it's higher than the dew point. The air temperature has to be higher than the dew point. Another way to think of this is, hey, if the air temperature is lower than the dew point, that would mean that the relative humidity is more than 100%, and we know that you can't be more than 100%. So that's something to keep in mind as well. All this being said, there are two ways that we can reach that dew point, and the first way is to cool that air. So I'm going to take this. Now you might be saying, well, how are you going to be able to get all the air outside to cool down? Like, do you take a big fan or a big air conditioner and you cool that air down? No. We already talked about the best way to cool air, and that's to bring it somewhere. It needs to go somewhere. And cold air can be found where? Well, it can be found above us. How do we get air to go up? Well, it needs to be less dense. So cool air temperature, we got to make it rise. If we can make it rise up, then what's going to happen? Well, the air is going to go cool. It's going to expand. It's going to condensate, which is why we see clouds above us. And clouds are liquid. Condensation creates liquids. Okay, so we're going to cool that air temperature. So that's where I want to leave off. I don't want to go too far with this lesson, but just to give you an idea of this second idea of relative humidity. It's a percentage. How full is that air full of water vapor? And now if you're still confused and you're still trying to figure out this last bit right here, what is it based upon? Well, hopefully you recognize through the demo. If not, pause the video right now, go back to the demo and watch that again. What was the main factor in determining the percentage of humidity in the air versus how much it could hold? How much percent? What was determining the percent of how full that beaker was? Well, hopefully you understood that it was the size of the beaker, right? And the size of the beaker represents that denominator here. That denominator is based upon something. Oh, then in my demo, I labeled it out that the bigger beakers were high temperatures and the smaller beakers were low temperatures. So what is relative humidity solely based on? It's based on temperature. And through that, you know that every single day, that every single minute, that every single hour, temperature is changing. That means that relative humidity is changing. That means that weather is changing. And if you're putting the pieces of the puzzle together at this point, you're recognizing that the lower the relative humidity is, meaning the lower the percentage is, the nicer the weather is outside. Remember, it's not full. The gas tank's not full, so there's no condensation occurring. If anything, it's evaporation that's occurring. And there's no clouds above you because the air's got to be really, really cold to reach a dew point when the relative humidity is really, really low. So it's a really nice, no cloud, sunny day. Now, when the air is full of water vapor, the percentage is really, really high. That means more condensation is likely to occur. That means there's probably more clouds, and therefore there's going to be worse weather. Going back over, if I cool that air, kind of like what happens in San Francisco, that dew point is going to be reached, just like the soda can, cooling the air around it, just like a cold window condensating on the interior. When it rains outside, this is actually condensation on the inside of a window. Just like in summertime when you wake up, the water is really, really cold and it's cooling the air to the dew point, making a nice fog above the lake. Or like in San Francisco, where the ocean is always cold because they have the California current coming down from Alaska. This is why San Francisco is constantly foggy. Okay? Because air is cooled to reach the dew point where 100% relative humidity is reached, and condensation occurs on dust to make clouds and fog. Okay, we're going to talk about the second way to reach dew point in my next lesson to continue on with our conversation about the rest of this stuff. If you have any questions, please make sure to ask, and we're going to take a look at some more examples of this later. Thank you very much. Have a good one.